All right, today we're going to pull back the curtain on some really cool science, the hidden chemistry that makes our clothes just pop with these brilliant, intense colors. Seriously, it's a whole story of chemical attraction, rejection, and believe it or not, a little bit of matchmaking.
I mean, have you ever just looked at a super brightly colored shirt or something and thought, how in the world did they do that? Like, how do you get a color that vibrant to actually stick to a piece of fabric and stay there? Well, a lot of the time, the answer comes down to a really special class of dyes. And the hero of our story today? It's the basic dye. The secret to its incredible brilliance? Well, it's all about some really clever chemistry. We're talking about positive and negative charges, like tiny magnets. So what exactly is a basic dye? Well, to put it simply, its color comes from a positively charged particle. Scientists call this a cation. A great way to think about it is that the color itself has this tiny positive charge, kind of like the plus side of a battery. And that positive charge, it's the key to absolutely everything that happens next. Okay, now this is where it gets really fascinating. The dye actually starts out completely colorless. It's a colorless base. But then you introduce an acid, and boom, a chemical reaction kicks off that creates a colored salt. That acid is basically a light switch, flipping the color from off right to on. And you know what? Just like you can flip that switch on, you can also flip it right back off. If you add a strong alkali to the mix, the whole reaction just reverses. That colored salt turns right back into the original colorless base. So this brilliant color we see, it's purely a product of its chemical state. Pretty cool, right? But here's where things get a little tricky. As amazing as these dyes are, they kind of have a problem with commitment. Yeah, they're picky. They don't just bond with any old fiber that comes along. We have a problem of attraction. You see, with some fibers, like acrylic and jute, it's love at first sight, a perfect match. The dye bonds directly, no problem at all. But then you have cotton, one of the most common fibers in the entire world, and it basically just gives this dye the cold shoulder. So why the rejection? What's cotton's problem? Well, cotton is made of cellulose, and cellulose just doesn't have the negative charges that our dye's positive charge is looking for. Remember those tiny magnets? Well, there's no opposite pole to attract it. So without that, the dye has literally nothing to grab onto. It just floats away. So how do chemists get around this? How do they play Cupid? They bring in a matchmaker. Seriously. For cotton, the solution is this chemical agent called a mordant. And it does exactly what a matchmaker does. It acts as a bridge, connecting the fiber and the dye who couldn't connect on their own. And it's basically a three-step process. First, you have to mordant the cotton, say, with something like tannic acid. The best way to think about this is like putting a primer on a wall before you paint. It preps the surface. Step 2, you use a fixing agent to lock that primer onto the fiber to make sure it's not going anywhere. And then finally, step 3, with all that prep work done, the cotton is ready to be dyed. The basic dye now has something to hold on to. Okay, so that's the theory. We get it. But let's see how all this chemistry actually works in practice with a few different kinds of fibers. So first up, let's look at jute. Now, as we mentioned before, jute has a natural affinity for these basic dyes, so the whole process is way more direct. No need for that chemical matchmaking we just talked about. The process for jute is pretty straightforward. You basically just crank up the heat to between 80 and 100 degrees Celsius and let it cook for about an hour. It's really that combination of high heat and time that drives the dye deep into the jute fibers. All right. Next up, let's talk about a protein fiber, like wool. The process is kind of similar, but you have to make a few key adjustments to account for wool's unique chemistry. So for wool, the temperature is set at 90 degrees Celsius. But here, a new ingredient is added to the mix, salt. And you might be wondering, why salt? Well, it acts as what's called a leveling agent. It encourages the dye to spread out nice and evenly, instead of just rushing to one spot and clumping up. This is the big secret to avoiding a patchy, blotchy color. And finally, we get to acrylic. And honestly, acrylic is the perfect partner for basic dyes. The bond they form is just super strong, which is what allows for some of the most brilliant, vibrant, and long-lasting colors you can possibly find. Now, dyeing acrylic requires a lot more control. The temperature has to be ramped up very slowly in different stages. It's this careful, steady increase up to 85 degrees that's so important. It's all about giving the dye enough time to absorb smoothly and evenly, which prevents any weird creases or splotches in the final fabric. It's a much more delicate process. Okay, so we've seen how basic dyes work and how they're used in the real world. But how do they stack up against other dyes? Where do they fit in the bigger picture? Let's do a quick comparison with some other members of the great big dye family.
You can really see the key differences here. The biggest one is where the color comes from. For direct and acid dyes, the color comes from a negatively charged anion. That's the total opposite of our basic dye's positive cation. And you can also see how their natural affinities are different. Basic dyes are really the odd one out, often needing that mordant matchmaker to get the job done.
So, let's wrap this all up. What are the main things to remember? Well, first, basic dyes are your ticket to exceptionally brilliant colors. Second, that color comes from a positive charge, a cation. They bond super easily with stuff like acrylic and jute, but for cotton, they need that chemical matchmaker, the mordant. And finally, the exact recipe for how you dye something really depends on the specific fiber you're working with. You know, the science of dye is just a perfect example of how this complex, fascinating chemistry is hidden in plain sight. I mean, it's right there in the clothes we wear every single day. It kind of makes you wonder, doesn't it? What other hidden chemistry is out there coloring your world?